Good afternoon, everyone. Today we're going to continue talking about transformations. Although I thought I'd kind of backpedal a bit, we're going to go over some of the same stuff in a bit more detail. Okay, because I know some people are going to give me the raised eyebrow there, like, what are we doing here yesterday? So yeah, we're going to talk a little more detail. First, I'm just going to show you a little demonstration on Desmos again. Okay. And I've picked a different curve this time because I think it will show what's going on a little more easily. So we haven't talked about the curve of sine in detail, although I know the other day when we were playing, we had it up there. Okay, right? So I'm just going to show that first. Right? That's what the sine curve looks like. Okay, so in our transformations, okay, we know that first thing, the a value is some kind of a vertical stretch. Okay, so as I play with the value of a, and again, hope you're not trying to copy this down, it wouldn't work too well. Right, as a gets bigger, this curve just gets taller and taller and taller, stretching it out vertically. Right, so for example, on my original curve, when a was 1, so it doesn't really change anything there. This is too finicky. Anyway, when a is 1, it was 1, right? But as I make this large, it stretches up. Okay, when a is between 1, I'll get the reference curve on there. Okay, right, when a is less than 1, it gets shrunk. Okay, when it goes negative, it flips the curve over, right? So now it's been flipped over the y-axis. I got the mirror image, and it starts to stretch out again. Okay, so that's what's happening with the value of a. It stretches, it's pulling that thing up, or when a is less than 1, it's kind of squishing it. Okay, so that's what a does. Okay, we talked about D and C yesterday. So D is the horizontal one. Okay, and this is the one, it's a little weird to read. Okay, it is because it says minus D in the general form. So, for example, if D, right, if the value of my shift is, say, positive 2, in the equation, it says x minus 2, because x subtract positive 2. That's how it gets written. And it can throw people off a little bit, right? As I make D larger, you can see it's sliding to the right. Okay. As I bring it back, okay, it slides to the left as I keep decreasing D. Okay, the only thing being, right, is it kind of does the opposite of what you think. Right? In the equation, when say D is, 2.4, it's moved to the right, but I would be writing that in my equation as minus whatever that number is. Okay, so that's what's happening there. Okay, the plus C, right? We talked about that one. That just moves it up and down. So when C is positive, okay, the curve slides up. Okay, and when C is negative, the curve slides down. Okay, that one kind of does what you expect it to. Okay, when C is positive, it goes up. C is negative, it goes down. Okay, so those are the ones we reviewed yesterday, because you would have talked about them sort of when you did quadratics before, right? Because the left and right part is linked to where the vertex is, okay, and the stretch changes the shape. Okay. So I was asked by a couple of people yesterday, well, what if you have something multiplying x in that bracket? So we didn't talk about that. Well, let's have a look. What does it do? Here's b equals 1. I didn't turn it on. Let's try that again. Okay, this one is the loaded spring one. Yeah, when b is 1, okay, my original curve. Okay, when b gets larger, there we go. As b gets larger, I've taken my curve and I'm squishing it towards the center. So it's a horizontal compression. As b gets bigger and bigger, this gets more and more sandwiched in the middle. Okay, we'll start moving back out. So now b is around 1, it's matching up. Okay, when b is smaller than 1, it gets stretched out some more. Okay, it's getting wider and wider in the horizontal direction. So it's a horizontal stretch. Okay, briefly at 0. And then when I hit the negatives, it's reflected across the y-axis. We have a mirror image kind of left-right here. So that's our last transformation, okay, is that if you multiply x inside that bracket, okay, you get this horizontal stretch or compression, depending what the value of b is. Okay, so I hope that demonstration helped a bit, because I think it's a little easier to see what's going on with the sine curve. Okay, so there's going to be quite a bit of writing here, so brace yourselves. Okay, get ready to get your pencil sharpened, and here we go. So given a function f of x, this is going to look a lot like the definition we had yesterday. The function y equals a f of b times x minus d, and then plus c at the end. Okay, this is the general form of a transformation. Kind of all the possible things you can do with transformations. Okay, so now we're going to take a couple minutes to talk about each one of those things in detail. I think probably in better detail than we did in yesterday's note. So we're going to start with the familiar ones and then move into the horizontal stretching compression last. Okay, so here we go. So we already talked about this one. A is the vertical stretch or compression. Okay. And again, you've seen that before in parabolas. Okay, the idea being that if my base parabola, maybe say looks something like this, right? Y equals x squared kind of looks like that. Okay, if I am having a stretch, okay, I might end up with something that looks like this. Okay, I've taken the output values and multiplied them by something, and that stretches it out. Okay, we talked about this yesterday, right? If the magnitude of A, okay, is bigger than 1, okay, so it's stretched. It gets pulled up more and more. Okay, and it's by a factor of A. So if A is 5, it's being multiplied by a factor of 5. That's how much is being stretched out. Okay, if A is between 0 and 1, we call that a compression. Okay, because instead of being pulled up, it's kind of getting flattened a bit. So it's being pushed down. Okay, and that shouldn't be y, that should be x. Okay, if the a value is negative, okay, then that means we're going to have that flip, right? It reflects over the x-axis. Okay, and last but not least, how we apply this. Okay, this transformation is applied by multiplying the output values by a. Okay, and I guess to try to show what that means, okay, if I think about its position in the function, right, a times f of x. Let's say I wanted a specific value of my function, right? Like what's f of 2? So this expression now becomes a times f of 2. Okay, what does that mean? Right, well, I'm going to figure out what f of 2 is, right? I input 2, okay, into my function. I get an output of some kind. You know, maybe at 2, if it's that parabola, it turns into 4. And then I'm going to multiply by a after, right? So it's the output of the function that gets multiplied by a. Okay? And right on a graph or in a table, what's our output? Okay, the output value is the y values, they're the range. Okay, so that's why we were multiplying those values by a. Okay. All right, here comes the next blurb. Okay, we're going to jump over to C and stick with the vertical stuff for now. So C is the vertical translation. Okay, so if the value of C is positive, we know it's going to go up. Okay, and if c is negative, it's going to move down. Okay, so again, if kind of as a reference point here, I draw my axis, okay, and I have something like y equals x squared, right? We know that the value of c just moves it up and down. Okay, so if c is positive, okay, right, it's going to slide the whole thing up, right? If c is negative, it's going to slide the whole thing down. Okay, it's moving it in some direction. That's what's happening. Okay, so how do we show this in a table? Okay, well, we're really adding c to our output. Okay, so again, if we think about what's going on, right, in terms of the transformation, that's the last thing on the list, f of x plus c. So if I wanted to find a value of something, right, what is f, this thing at 2? Well, I would say, what's f of 2 plus c? So I look up my function value at 2, but then I have to add c. So that's why the thing moves up and down, okay? And that's why we're applying it to the output, okay? It comes outside of those function brackets, so it's changing the output values, which are your y values. Okay. The third one we reviewed yesterday was the horizontal translation. Okay, and again, this one is awkward to describe just because of how the function and notation is set up for this. Okay, so even though it says minus in those brackets, right, I should say because of that, that's what tends to mess people up. Okay, if d is positive, it moves to the right. Okay, however, in the brackets, so like if my d value is 3, okay, in the brackets, it's going to look like x minus 3. Okay? And it's counterintuitive, like it is. Okay, but my d value is really 3 there. It's a positive number. It moves to the right. Okay, if d is negative, it's going to move to the left, because what happens is, if d is, say, like negative 4, in that notation, it's x minus minus 4. Oh, so it gets written as x plus 4. Right? It looks like the opposite of what we are expecting. Okay. So this transformation is applied by adding d to the input values, okay, because that's what I'm changing is my inputs. Again, however, because the expression looks like x minus d, it kind of looks like it's the opposite of what we think it would be. Okay. I know I think I explained that a little bit differently yesterday, so hopefully that helps there. Okay. But that's what's happening here. So if there's my function, right, or my axes, there's my x squared. Okay, if I had something like x minus 3 in the brackets, well, that really means the d value was plus 3, and I'm moving to the right 3. That's how that works. Okay. Again, and it's a little bit weird, right? But from vertex form, it was the same thing. It's the opposite of what you think it might be. Okay, so the new one, okay, the horizontal compression, that is also a little bit counterintuitive to what you think it might mean. Okay, so value of B is the horizontal compression or stretch. Okay, if B is bigger than 1, or the magnitude of B is bigger than 1, it is actually a compression by a factor of 1 over B. So for example, if my expression looked like f of 2x, it is actually a compression by 1/2. Okay, so it's moving in to half of what it was horizontally. Okay, if b is between 0 and 1, it's a stretch of 1 over b. Okay, because, right, so if I had f of 1/3 of x, okay, this is going to get messy for a second here. Well, that means it's 1 over 1/3. Okay. Okay, now we don't need to write the double fraction. So when we bring this around, right, that means I'm dividing by 1/3. So that would be the same as 1 times, right? To multiply, divide a fraction, you invert and multiply, and I just get 3. Okay, so even though it says 1/3 there, this is really a stretch by a factor of 3. Okay, because that's 1, it's the reciprocal of that. If our b value is negative, it will reflect over I got both of those backwards. It will reflect over the y-axis. It's horizontally reflecting. Okay. The way we apply this to a point table, okay, is that we are dividing the input values by b. Okay, again, it's a little counterintuitive. It's the opposite of what you might think. Okay, or it's the same thing as saying you're multiplying it by 1 over b. Okay, that was a lot of definition work. Okay, we're going to do a couple quick examples to reinforce what's going on. So here's the first one. Okay, so you're going to put out some functions. I just want you to state what transformations you see there. Okay, so what do we actually have here? Okay, so our first function is y equals 2 f of x plus 1 minus 3. Okay. As we go from left to right, so this is our a value. So that would be a vertical stretch by a factor of 2. Okay. Inside the brackets, okay, this is our horizontal. Now, this is the part that's a little counterintuitive. I know it says plus 1 when you read it, but my value of d, okay, is really minus 1. Okay, it's the opposite of what you see there because the form is x minus whatever. Okay, so this means we have a horizontal shift to the left by 1. Okay, our c value, okay, is -3. So this means we vertical shift down 3. Okay, those are all the transformations that are there. Okay, here's the next one. Y equals f of 3x plus 4. Okay, so there's no a value that we can see. Okay, inside there's my b value, which is 3. Okay, that's bigger than 1. So this is actually a compression. Okay, this is a horizontal compression by 1/3. Okay, it is 1 over the value of b. Okay, and then plus 4. Okay, that is a vertical shift up 4. Okay, last one. Y equals 3 f of 1/2 x minus 3. Okay, so right here, my a value is 3. So it's a vertical stretch by a factor of 3. Okay, f of 1/2 x. Okay, that is a horizontal stretch It's between 0 and 1 by a factor of 2. Okay, right? The reciprocal of a half is 2. So it's actually, okay, last but not least, we'll do this an example of actually transforming a function with a point table. So given that a function r of x is the square root of x, we're going to graph r of -2 x minus 4. Okay, so let's note what our two translations are. I guess kind of 3, but here we go. Okay, my b value is -2. Okay, so that means I have a horizontal compression by 1/2. Okay, I also have a horizontal reflection okay. Now those two things can kind of go together when we do a transformation. Okay, and finally I have a horizontal shift. Okay. Now again, the d value, right, the actual shift value is 4 because it's minus d, it's 4. So this is going to be to the right 4. Okay, I have all my pieces. So to get the graph, we're going to run through the point table method here. So I'm going to start with r of x. So some nice points to work with from the other day are 0, 0, 1, and 1, and 4, and 2. Okay, so my initial graph looks something like this. Okay, and I'll start applying the transformations. Okay, so I'm going to group a couple of them together. Okay, the first thing is the horizontal compression and reflection. So let's be -2x. So in our list there that we developed, okay, we said the way we apply this, okay, it applies to the inputs because it's inside those brackets. Okay, we're going to basically divide everything by -2. Okay, or not everything, the x coordinate, right? My input values get divided by -2. So 0, 0 stays the same. Okay, 1 divided by -2 is -1/2. And 4 divided by -2 is -2. Okay. The remaining transformation is the horizontal shift. So r of -2 x minus 4. Okay, so the d value is 4, so I'm adding 4 to each of those. So 0 plus 4 is 4. -1/2 plus 4 is -3/2. And then, so that's not negative, is it? That would be positive 3/2. Okay, 2 and 2. Okay, so I've got my points now. So on my final graph, I got a point at 4 and 0. I got, sorry, that's a 1. Okay, I got 3/2, which is right beside there, and 1, and then 2 and 2. Okay, so my graph looks something like this, and there is my transform graph. Okay, so hopefully that clears things up a bit. Okay, again, if you're still not feeling unsure, make sure you ask me questions during tomorrow's class. We'll do one more thing with this and finish it up. Okay. So practice work. Okay. Same section. I know you did some of these questions already, like I think in number 7 and maybe number 8, okay, from yesterday. So anyone you've already done, don't worry about it, okay? But numbers 1 and 3 kind of more just are talking about reading the transformations, and 7 and 9 is practicing the skill of transforming. Okay, so please work on that for the rest of the class. Thank you very much for watching, and I will see you tomorrow.